All right, guys, I'm just going to walk you through how to do some of the things from Chapter 7. So first thing we're going to do is from 7.1, and this is the graphing section for exponential equations. So I am going to walk you through how to graph something like this. Y equals 1.5 times 2 to the x plus 1 minus 3, something like that. Okay, so what we do, ignore all that stuff on there. What we do is we hit menu, and then number 1 for actions, and then number 1 again for define. And I guess normally, I'm sorry, let me scratch this. This will normally be given to you as f of x. Okay, because that's the way you're going to type it into the calculator. So you'll type in f of x, make sure you've got the parentheses right and everything, equals, then you'll type it in exactly the way it's written, 1.5, with the 2 in parentheses. And then you'll hit your little caret key, so you can type in a power, x plus 1, and then make sure you hit tab, and then so the minus 3 ends up kind of separate from the x plus 1. And then hit enter in your calculator, we'll just say done. That just means it's stored the function in. And then we're going to make a table. Okay, so this is just kind of a tentative table. You might have to add some stuff to it. You're always going to start with this. All right, with these 5 values, and then I'll explain how you would know if you need to do more on either side. So we type in the letter F, and then first put the negative 2 in parentheses, and we get negative 2.25. Then type in F of negative 1, and then we get negative 1.5. I'm just going to type a bunch of them in right now. All right, so those are some values. So we've got negative 1.5, 0, 3, and 9. Okay, so those are some values, and I think this is a pretty good picture. Let's start to graph just to double check. Okay, so we go up to 1, 2, down to negative 1, negative 2. We need to go up to 9. Okay, and then down to about negative 3. We got on to negative 2.25. So at negative 2, we're down at negative 2.25. And negative 1, we're at negative 1.5. 0, 0, right at the origin. 1, 3, and then 2, 9. All right, so we get a pretty good picture of the exponential part happening over here to the right. Let's do one more point just off to the left. So let's also plug in negative 3, just so we can get an even better picture. All right, so if we do f of negative 3, yeah, then we get negative 2.625. Okay, so maybe right around there. So it kind of glides this way, and then it's going to run through these points, and then you can see it starts growing very, very quickly off to the right-hand side there. All right, so our graph looks something like that. You also have to come up with domain and range. You will be explicitly asked. Don't worry, you won't have to remember that you have to write that down. So for domain, for all of these exponential functions, domain is all reals. So you can just remember that every time. I'm allowed to plug in anything that I want. And then the range, remember, is the y values that you get out. So you can see if I were to keep going off to the left, and I'll show you, if I did f of negative 4, if I did f of negative 5, f of negative 6, you can see these numbers are getting closer and closer and closer to negative 3. They're never going to actually hit negative 3, nor will they ever be below negative 3, which means for our range, any y value that's above negative 3, I'll end up hitting at some point. Now another way is from looking at this. The minus 3 on the outside tells you what this number is going to be right here. The reason this is greater than is because this is like a normal right side up exponential equation. If I had a negative in front of this number, that would mean that my graph was upside down, and that would mean that this would be a less than instead of a greater than. But for right now, it's everything greater than negative 3. I can find my number negative 3, and everything above that line is shaded. All right, so 7.1. Got that under control. 7.2, we looked at some exponential equations. All right, so I'm going to walk you guys through a couple of those, just some different equation examples. So some 7.2 stuff here. Box and 7.1 up there. So 7.2 stuff, we're solving some equations. So let me give you an example. First one looks like this. 8 to the x minus 2 equals 1 over 16. So this first type of exponential equation that we learned, we had to figure out how to put them in terms of a common base. So 8 and 1 over 16, they're both powers of 2. So for 8, we're going to write it as 2 cubed, and then I still have my x minus 2 out here. And then for 1/16, it's 2 to the negative 4th. Remember, anytime I have fractions, it ends up being a negative exponent. So the next thing I do on the left is I'm going to distribute that 3 to the x minus 2. And then on the right, nothing's changing there. So I have this property that tells me if I have the same base right here, I can just set their powers equal to each other. All right, which is exactly what I'm going to do. I'm just going to set that power on the right equal to the power on the left. And then I can just do just a little bit of algebra here. Okay, so I end up with 2/3 would be my answer. A couple other things I can do in this section. I also had inequalities, which are very, very similar. So for inequalities, I could see something like this. Okay, so inequalities are very, very similar. I have to write them as a common base. So 27 and 243 are both powers of 3. 27 is 3 to the 3rd, which means 1 over 27 is 3 to the negative 3rd. And then 243 is 3 to the 5th, which means 1 over 243 is 3 to the negative 5th. Okay, then same next step is up above. See here where I distributed the 3. It's exactly what I'm going to do here. I'm going to distribute this negative 3, and I'll get negative 6x minus 3 for this power. Then here I'm going to distribute the negative 5, and I'll get negative 15x plus 10 for this power. Now, my setup is basically the same. I have another property, this is a property of inequality though, that tells me if these two are the same, I could just set this power, then whatever the inequality is, compared to this power. So I just take this power right here and set it less than or equal to negative 15x plus 10. All right, so now, just like the one up above, just a quick little bit of algebra here to get the x by itself. Okay, so I get a 9x is less than or equal to 13, so it'll just be a nice weird fraction, just x is less than or equal to 13 over 9. Okay, then there's one more thing that we can do in section 7.2, and that's coming up with an equation. Okay, so say I give you 2 points, like 0, 5, and 6, 320, and I ask you to write an exponential function for the graph that passes through those 2 points. The exponential function looks like this, so you need to have that much memorized. We're going to try to find A, and we're going to try to find B. So we're going to start with this point right here. This is x, this is y. So we're going to plug them in for x and for y. So y gets replaced with a 5, and then a times b, and then we're replacing the x with a 0. So b to the 0 is just 1. Because remember, anything raised to the 0 power just gives us 1. And so we know that 5 is just equal to a times 1, which is just a. So my updated version of the equation, I know that a is going to be 5. So I got half of it. I still need to figure out b. So now I'm going to use the second ordered pair. I'm going to plug in 6 for x. I'm going to plug in 320 for y. So I've got 320 equals, but now I know what a is. I still don't know what b is, and I'm plugging in a 6 for x. All right, so now I'm doing whatever algebra I need to do to get b by itself so I can solve for it. So I do 320 divided by 5. That gives me 64. And then to get b by itself, I'm going to take the 6th root of both sides. Okay, so the 6th root, I hit Control and then the square root button. That way I can type in my own index. 6th root of 64 is 2. Okay, so that means that b equals 2. So I know a, I know b. I can plug those into this equation right here, and I get y equals 5 times 2 to the x. Now remember, you cannot multiply 5 times 2. It doesn't work like that, because 2 is being raised to a power, then I multiply that by 5. So it would not at all be the same as 10 to the x. So So be very careful with that. I know it's tempting. Okay, let's look at some stuff from 7.3. 7.3 is when we learned about logs, and we first started by translating back and forth between log and exponential form. So let's say that I gave you this. Log base 3 of 243 is equal to 5. Let's say I asked you to write an exponential equation that was equivalent to that. The exponential equation would look like this. I take my base, which is 3. My power is then over here, and then equals 243. Okay, and hopefully we recognize this as being a true statement. So if I give you this and ask you to write it as an exponential equation, you write this. I could also give you something like this and ask you to write it as a logarithmic equation. Okay, so I could give it to you in exponential form. If you want to write it in log form, you write the word log first, then this first number is your base, and then the other two trade. So log base 6 of, then you go to this one, 1 over 216 equals -3. Okay, so it's a back and forth process, so we should be able to do it either way. Okay, now in this section we also graphed logarithmic equations. Oops, f of x again, sorry. Okay, so I could ask you to graph that. Now we've got a process that we've been using for this. We've been going off of these 3 original points on a logarithmic graph. Okay, so a logarithmic graph, first of all, always has the point 1, 0. All of them have the point 1, 0. So I'm going to write our old points here. And then they also all have the point b comma 1. And they also all have the point 1 over b, -1. All right, so those are my old original points. What I'm going to do is I'm going to take the transformations that I have right here and rewrite a new set of points. And that's how I graph my logarithmic function. Okay, so the first thing I'm going to do is take a look at the x's. The only thing that affects the x is what you see inside the parentheses. Okay, everything else is going to affect y. So what I have inside the parentheses is an x plus 3. Now remember, x lies, all right? X lies. So you have to make sure that you're actually doing the opposite. So plus 3 seems like you'd add 3, but you actually do the opposite and you subtract 3. So I'm going to write all my new x values here. So first of all, these right here, I use my base. And so these become 1, 0, and then I have 4, comma 1, rather than b, comma 1. I just wanted to write the generic one. And then here I have 1 over 4, comma -1. So those are my actual official points based on this base. Okay, so now I'm going to subtract 3, because x lies. So 1 minus 3 is -2. 4 minus 3 is 1. And then 1/4 minus 3 is -2 3/4. Okay, you could use a calculator on those if you're doubting me on anything. Okay, and then everything else that's not directly in sets of parentheses affects the y. So this right here is going to affect the y, and this right here is going to affect the y. So I always go left to right. So first I'm going to multiply by 2. Then I'm going to subtract 2. So I start with this value. I start with 0. I'm going to multiply by 2, still 0, and then I subtract 2. So that would be a -2. Okay, now I move to this value, 1. I'm going to multiply by 2. 2 times 1 is 2. And then I'm going to subtract 2. 2 minus 2 is 0. Okay, then I move on to this one, -1. -1 times 2 is -2. Minus 2 is -4. So that's where I get all 3 of my new points. I am going to plot those points. Okay, so this point, I have the point -2, -2. And that's this point right here. I have the point 1, 0. This point, and then I also have the point -2 3/4, -4. Okay, right around there. So my logarithmic graph is going to look like this. Okay, and you should make sure you know the general shape, because if you know the shape looks like that, it's going to be a lot easier for you to graph it. Okay, so it looks like that. So that's 7.3 stuff. Let's take a look at 7.4 and see what we need to practice there. All right, so 7.4 stuff, we are still working with logs. and we started doing some log equations and inequalities, okay? So let's look at a couple of examples of these. So log equations, there's two different types of log equations we could be working with. Let's say we had something like this versus something like this. I'm going to kind of write them both on the same general area so you can see the difference I'm talking about. Okay, so hopefully you'll notice a big difference. This one on the left only has a log expression on one side. This one on the right has a log expression on both sides. Either way, they're log equations. Starting with the one on the left, if you only have a log on one side, your technique is to turn it into exponential form. So I start with my base is 2. Raise it to my power, which is 3, and then set it equal to this inside piece, which is 2x. So that's pretty easy. So 2 cubed is 8. 8 equals 2x, and I can divide both sides by 2. Now, anytime you're dealing with logarithmic equations, you have to make sure that whatever you're plugging in is going to be positive. 2 times 4 is positive, so that works. Now over here on the right-hand side, this one's actually pretty easy as well. Whenever I have two logarithmic expressions, log over here, I have a logarithmic property of equality that tells me that if these two pieces are equal, then these two pieces have to be equal. So all I have to do is set the x plus 17 equal to the 3x plus 23, and I'll be able to solve. Okay, so I'm going to subtract x from both sides, so I can move them from the left, and then I'm going to subtract 23 from both sides, so I can move those from the right. Okay, 17 minus 23 is a negative 6. 3x minus x is 2x, and I can go ahead and solve. So I get x equals negative 3. Just because this is a negative number doesn't mean this will be a negative number. Negative 3 plus 17 is still positive, and 3x plus 23 is still positive. So that works. Okay, so those are the equations. In this section, we also had inequalities. Okay, so some of these inequalities, these are very similar to the idea that, one of them could have just a log on one side and then one of them could have a log on both sides. So I want to make sure you see an example of both of these as well. Okay, so this one, you do basically the same thing. You're going to convert it into logarithmic form, except this one's a little bit weird. You've got these properties of inequalities that you did write down on your notes. When you do these, you actually want to start with this part. You always want to start with the inside part just to make sure that the inequality ends up in the right direction. So if you start with this part, then you get to keep this inequality right here. Then you do the 5 to the third. All right, so when you're doing the inequalities, you kind of do them backward, or you don't have to do them backward, and you could just flip the sign. Flip the less than to a greater than. But I think it's easier to do it this way, then the signs are matching. And then if you have a less than, you also have to throw in this piece right here, just to ensure that whatever you're plugging in is greater than 0. If this is a greater than, you don't have to worry about that part. All right, so now let's finish this off. 5 cubed is 125. All right, and then remember the way these three-piece inequality works. Whatever you do to the middle, you have to do to all three sides. Okay, and then we're going to divide all the sides by 4 to get that x by itself. So we've got 3/4 is less than x is less than, and then this comes out to be a 32. All right, so as long as it's bigger than 3/4, you won't be plugging in anything negative here, and then anything smaller than 32 will make that inequality work. Okay, now this one, much simpler. This is the same sort of idea as the one on the previous page. If these log pieces match, all I do is set the left piece less than, or whatever this symbol is, the right piece. So you're basically just dropping those logs. All right, so I'm going to subtract x from both sides. I'm going to add 4 to both sides. So I get 2x is less than 5, and then I'll divide 2. So I get x is less than 5/2. And then with these, I've got to make sure that both of these insides are coming out to be greater than 0 as well. All right, so this one right here, the 3x minus 4 has to be greater than 0. So that means x has to be greater than 4/3. And then with this, I have to set the x plus 1 greater than 0, and that means x has to be greater than negative 1. All right, so I don't need to worry about this, because as long as x is greater than 4/3, I know x is greater than negative 1. So I have to be greater than 4/3, but also less than 5/2. So I'm going to set up a 3-piece inequality just like the one I have on the left. Okay, so that's 7-4. All right, so now we move on to 7-5. We've got some log properties that we can work with. So 7-5, our log properties, we are going to do, let's see, I'm actually just going to write the log properties down. And just have you basically memorize those. We'll do one equation that'll kind of demonstrate these, but one of the things you'll have to do is the ones from the quiz, like where you're given, oh, like log base 12 of 3 and log base 12 of 7, and then you'll have to come up with log base 12 of something else using these properties. But as long as you've got these properties memorized, you should be able, to be just fine using them and everything like that, okay? So let me give you an example of an equation that you could do with these. So an equation would be something like this. Okay, so you use some of the properties. First of all, on the left, you use the property that tells you this can move inside as an exponent. So you do log base 4 of 6 to the 3rd minus log base 4 of 8. And then over on the left-hand side here, you've got subtraction in the middle, and subtraction should lead you to this property right here, which means you combine them up as one log with a quotient inside. Okay, and then finally, now that you only have one log on each side, you can just set the insides equal to each other. Okay, and 6 cubed is 216 divided by 8. I don't think that's anything that comes out even. It might. Let's find out. 216 divided by 8. Oh, it does. It's 27. Okay, so now let's look at 7-6. We're getting there. We've got just some 7-6 stuff and some 7-7 stuff. All right, so 7-6 is all about the common log. We did some common log things. We did some solving equations. That was the big one. So let's look at something like this. 6 to the x plus 2 equals 18. We did ones in 7-2, I believe, where we could write them as a common base. These ones you cannot write them as a common base. So what you do instead is you start by taking the log of both sides. Okay, so again, if you cannot write them as a common base, you start by taking the log of both sides. Then you use one of these properties you've got written down that tells you that this x plus 2 can be written out front as like a coefficient of sorts. So make sure you keep it in parentheses, otherwise you might throw yourself off. Okay, now we're trying to get the x by itself, so I'm going to divide both sides by the log of 6. Okay, and then let me show you very, very carefully how you need to plug that in. So set up a little fraction, and you'll do log of 18. If you just skip over that first box, it'll assume you mean 10, which is the common log. Okay, so you have to type it in like that. You can't divide the 18 just by 6. You have to do a separate log in the numerator and a separate log in the denominator. So we get about 1.6131. We always want 4 decimal places with these. And then you subtract 2 from both sides. So we take that number and we subtract 2. And we get negative 0.3869. Okay, so that's what you need to be able to do from 7-6. Actually, let me add in one more thing. We also did change of base in 7-6. So change of base, if I give you something like this, the directions will read express each logarithm in terms of common logarithms. So this is just that change of base formula that tells you that this is equal to the common log of 200 divided by the common log of 12. Common log of whatever this number is divided by the common log of whatever this number is. And then you type them into your calculator, basically the same as what I just did. So common log of 200 divided by the common log of 12. All right, we get approximately this, 2.1322. Okay, so that's the change of base formula. The last section we have was 7.7, and it's basically, the only new thing here is that we have a new base, and that new base is base E, which we talked about, all right? So in 7.7, first of all, you can translate back and forth between exponential and logarithmic form. So this is exponential form. If you're asked to write a logarithmic equation, you start with log base E, which we write as ln, and then of 7 equals 2x. Okay, so that's log form. You could also go back the other direction. Like say I had natural log of 42 equals x. I could ask you to write that in exponential form. So I start with the base, which since this is natural log, the base is e, and then raise it to this number as a power equals this number. Okay, so same thing we did in actually 7.3. We just have a different base. So you're translating back and forth between log and exponential. Okay, another thing that we did were different equations and inequalities. All right, so just two more examples here. So here's an equation. So basically we've got this exponential part, which is just this part right here. We have to get that part by itself before we do anything too fancy. So we're going to start by subtracting 2 from both sides. So we get 8. Then again, to get it by itself, we have to divide by 3. So I get e to the 2x equals 8/3. Now in this, I have two different bases. I have a base of e over here, and I have a base of 8/3 over here. What I told you guys in 7.6, or just that last section, you have to take the log of both sides. Since we have a base e, we're actually going to take the natural log of both sides. Okay, now we talked about this. Natural log and e are opposites of each other, and so they cancel each other out. We know the natural log of e is just 1, and so all I have left over here is a 2x, and then I have the natural log of 8/3 over here on the right. Very last thing I'm going to do to get the x by itself is divide by 2, so I'm going to plug that into my calculator. So I'll show you. So we do the natural log, I hit control and then e to the x, type in my 8/3, and then separate from that I'm going to divide it by 2. Okay, so I get about 4 decimal places, 4904. Okay, so that's my answer for the equation. I'm going to do one example of an inequality, and then that'll be it for us. Okay, so this is very similar to one that we saw in maybe 7.5, 7.4. When we're doing inequalities, you actually kind of work backwards. We start with this piece right here, then less than when you're turning it into exponential form. The base here is technically an e, so I write e, and then my power is 2. Okay, so I'm going to do whatever I need to do to get this x by itself, so I'll start by adding 1. So I get 4x is less than e squared plus 1, whatever that is, and don't worry, I have a calculator for it. Divide both sides by 4, so I'm going to get some funny decimal value. So it looks like this, e to the second plus 1 divided by 4 is that value, whatever that value is, 2.0973. And then remember with these inequalities, I also have to make sure that this is going to be positive. So I'm also going to set that inside greater than 0, which I always have to do with these inequalities, because I'm not allowed to plug in anything that's negative into a logarithmic equation. Okay, so I also get that x has to be greater than 1/4. So it has to be greater than 1/4, but also less than this number. So I'm going to set up a 3-piece inequality. Okay, so there we go. So that's something that you could see from 7.7. So hopefully you guys got a good taste of some things that you could see on your test. So feel free to come in the morning if you need any additional help.